We're moving into section 16.3 in the 6th edition of Stewart. This is where we find out that the fundamental theorem of calculus still works, subject to the appropriate hypotheses. First, I want to start with an example. I want to take a path from 0, -1, up to 1, 1. I'm going to take two different paths, actually. I'm going to start with a straight line path. And I want to compute the path integral over c, that's c, of 3x squared, 2y dot dr. So the first thing I have to do, pause and work this out for yourself, is parameterize that curve. Parameterize my path c. So c will be given by r of t equals, let's see now, I have 1 minus, well, in the x direction I have 1 minus 0, and in the y direction I have 1 minus a minus 1, times t, plus my initial point. We're going to travel up the curve there. So plus 0, comma, -1. And what I need for dr, so if you didn't already work through the whole problem when you paused the first time, pause here and work through the rest of the problem and see what you get. Here's my attempt. What I need for this is r prime of t, which will just be 1, 2. So I'll do the path integral from 0 to 1 of 3x squared, x is t plus 0, comma 2y, y is 2t minus 1, dot 1, 2 dt. And that will be the integral from 0 to 1, but now I can multiply all this out. I'll have 3t squared plus, 8t minus 4 dt. And that's an integral I can do. This is Calc 1 land now. You just get t cubed plus 4t squared minus 4t from 0 to 1, which is 1 plus 4 minus 4. So it just comes out to be 1. Now I want to know what happens if I want to travel along, say, this path. There's a different path. To do that, now I have to start over. I have to find the parameterization for the green path and then do all this work again. And that's a bother. Especially since I don't actually have much of an idea of how to parameterize that path. If I make it a parabola, I might be able to do something. Maybe it's not a parabola, maybe it's just some other kind of arc. I don't know what kind of arc. So this could be really hard. Instead, we're going to go with this new theorem that is actually an old theorem. This is the fundamental theorem of calculus for line integrals. And here's what it says. Let C be a smooth curve. So I need C to be reasonably nice. Given by r of t on closed interval AB. And let f be a function with continuous partials on the curve C. Okay, so that's our setup. We have a reasonably nice function on a reasonably nice curve. Then, path integral over C of the gradient of f dot dr. Remember, the gradient of f was one of our early examples of a vector field. The gradient of f dot dr is equal to f of r of b minus f of r of a. Now that's a wonderful theorem. It's wonderful for several reasons. The first reason is it looks just like the regular fundamental theorem of calculus. The regular fundamental theorem of calculus says, if I want to do an integral of a function, the first thing I have to do is find an antiderivative for the function. In this case, we have this vector field is our function. So what does antiderivative mean in that context? Well, it means an anti-gradient. I need to find a function whose gradient is the vector field I'm given. And if I do that, then I just have to figure out what happens to that antiderivative at the boundary, on the boundary of my region of integration. Now, here my region of integration is this interval. Or the region of integration is the curve C. And so the boundary is just the endpoints, R of B and R of A. So I find out what it does on the boundary, and I look at the difference there. And that's my path integral. That's the value of my path integral. So this looks just like the Calc 1 version, right? Except this is, instead of f of b minus f of a, it's f of r of b minus f of r of a, because I have endpoints on the curve C instead of endpoints of my closed interval. But the idea is exactly the same. Here's another wonderful thing it says. It says, if I'm doing a path integral of a continuous gradient field, like this, gradient vector field, my path integral is independent of path. It doesn't matter what C is. Look, there is no reference to C in the right-hand side here. Here's why that's wonderful. It tells me that when I want to do this green path, instead of doing that, if this happens to be the gradient of something, instead of trying to figure out a parameterization for my green path, I just find my anti-gradient and evaluate it at the endpoints. And it doesn't matter whether I take the green curve or the black curve. Either one will give me the same thing. That also means if for some reason I don't want to find my anti-gradient, but I know that there is one, I have to know there is one or else this doesn't make sense, then I could parameterize with a line segment. Right? If I'm given the green curve and say, oh, I can't parameterize that, I don't know what to do, I can instead say, I'll take this black path, because they're going to give me the same answer. Now you have to be a little bit careful with that. It must be the case that your vector field here is the gradient of something. If it's not, this theorem does not apply. You have to check your hypotheses. So let's revisit this example now with this theorem in mind. Example, redo. All right, I need a function, I need to show that my vector field there, the 3x squared comma 2y, is the gradient of something. So notice that 3x squared comma 2y is the gradient of the function x cubed plus y squared. Okay, if I take the gradient of that, I will get 3x squared comma 2y. And so, since I know what my endpoints are, I can say my path integral over C of 3x squared comma 2y dot dr is equal to x cubed plus y squared evaluated from 0, -1, my starting point, to 1, 1, my ending point. Where this vertical bar notation means the same thing it did in Calc 1. Plug this point into the function, and plug the lower point here into the function, and subtract. So here I get 1 cubed plus 1 squared, that's 1, I don't really need the parentheses I guess, minus 0 cubed plus -1 squared. Oh, sorry. 1 plus 1 is 2, generally speaking, and then minus the 1. And I get the same number, 1, that I got when I parameterized the path. So the question you ask yourself at this point is, which method would you rather do? Do you want to parameterize your curve, or do you want to find this anti-gradient and apply the fundamental theorem? I know which one I would rather do. All right, well, we're going to prove this fundamental theorem. The proof will help us see another reason that we should think of it as the fundamental theorem, besides just the result, the form of the result looking like the fundamental theorem. We're going to use the fundamental theorem from Calc 1 in our proof. So here we go. We're just going to calculate. path integral over C of the gradient of f dot dr, that is the path integral over C of fx comma fy dot r prime of t dt, which is, oh, and since I've gone to t's now, this should be from a to b. So this is the integral from a to b of fx times x prime. Let me go ahead and include one more step here just to be totally clear. All right, r of t is given by x of t comma y of t. So here's r prime of t. And now I do my dot product. So this is fx x prime of t plus fy y prime of t dt. And I'd like you to look at that for a minute. Pause here and look at that and see if you recognize what that is. This is an important expression that we have encountered several times now. Did you recognize that as the result of the chain rule? That is the derivative with respect to t of f of x of t, y of t. And then I'm going to integrate that with respect to t, right? If I take the derivative of this, I do the chain rule. I do partial f with respect to x dx dt plus the partial of f with respect to y dy dt. So there it is. And now, the fundamental theorem of calculus tells me if I integrate the derivative with respect to the same variable, I just get the integrand back. So this will be f of x of b comma y of b minus f of x of a comma y of a. And this is exactly by the fundamental theorem of calculus from Calc 1, by the ordinary single variable fundamental theorem of calculus. And now this x of b, y of b, that's r of b. And x of a, y of a is r of a. And that's what we were trying to prove. So this is wonderful. It says only the endpoints matter in this calculation. The path you take is completely irrelevant. So I could take that straight line path, I could take the arc, or I could squiggle around however I want, as long as the gradient is continuous. That is, as long as my integrand is a continuous function and is the gradient of some function. One thing that means is that we're going to have to figure out how to find anti-gradients. That is, a function whose gradient is our given vector field. Also, you may remember from, must be 16.1, a vector field is conservative if it's the gradient of something. So this theorem, this fundamental theorem of calculus for line integrals, is about conservative vector fields. If your vector field is conservative, then the fundamental theorem, and continuous, then the fundamental theorem of calculus for line integrals applies, and you can find a potential function for your vector field f, and just evaluate that at the endpoints and look at the difference. So that's what the fundamental theorem says. We need a few more topological notions. Here's one. Definition. A path C given by r of t on the closed interval AB is called closed if r of b equals r of a. So a path is closed if it begins and ends at exactly the same point. Now let's explore what this means. So let's suppose that we have a curve like this. Here's r of a, here is r of b, and C1 takes us that way, and C2 takes us around that way. So what I know from the fundamental theorem for line integrals is that path integral over C1 of gradient f dot dr is equal to the path integral over C2 of the gradient of f dot dr. Okay, those are going to give me the same thing. because they both have the same endpoints exactly. But here's another way I can think of that. Since C1 and C2 together make a closed curve, I can draw a conclusion about closed curves. So let's say C is equal to C1 minus C2. So C1 minus C2, remember negative C2 means traverse C2 but in the opposite direction. So C1 minus C2 means start at R of A, come on up to R of B, and then travel along C2 back to R of A. So C is a closed curve. Path integral over C of gradient of f dot dr is equal to path integral over C1 gradient f dot dr minus path integral over C2 of gradient of f dot dr. Our integral over minus C2 is negative path integral over C2. But these two path integrals are equal. So this is just 0. And what this tells me is another wonderful property of conservative vector fields. The path integral of a conservative vector field around a closed curve is 0. Exactly 0. Always 0. There's a physical interpretation for that. It says that the work done by a conservative vector field around a closed path is 0. So if I think about, remember gravity gives us a conservative vector field. So if I think about the work done by gravity in moving this pen all around like this, but back to where I started, the work that gravity does is exactly 0. Okay, it does negative work as I move up, does positive work as I move down, but all that matters is that I begin and end at the same place. So I do just as much work going up as I do going down, but they have opposite signs, so they cancel out. I said before that an open set is one that doesn't contain any of its boundary points. Here's another definition that's equivalent to that one, but that we're going to need to use for what's coming next. So a set D contained in R2 is called open if for each point P in D there is a disk centered at P. Whoa, that does not look like an E. Centered at P that is entirely contained, entirely contained in the set D. So a set like this, here's my set D, whatever point I pick, I can always fit a little disk around it that's entirely contained in D. Now, I need to not include the boundary for that to work. If I include the boundary, so this one is open, this one is not open, because if I include the boundary here, any disk I draw is partly inside the set and partly outside the set. But the definition here says there has to be some disk that's entirely contained in the set. Up here, no matter how close I get to the boundary, I can always draw some little teeny tiny circle around there because I'm not actually including the boundary. So I just make the radius of the circle smaller than the distance from the point to the boundary. But down here, if I have a boundary point, I just choose the boundary point, and then no matter what disk I have, it's going to be partly in and partly out of the set. A little more. D is connected if there is a path between any 2 points of D that is entirely contained in D. So a set like a disk will be connected because any 2 points I put in the disk I can find the path between, and that path stays entirely inside the disk. So here's one. Here's a set that's connected. Because no matter which 2 points I pick, there's a path that stays entirely inside of D and joins those 2 points. But if I take something like this, so this one is connected, connected. This one is not connected. Sure, if I pick 2 points over here, I can get a path between them. But if I pick a point in the left part and a point in the right part, there's no path joining those two that stays entirely inside the set. I have to leave the set in order to get from the first point to the second point. So that set's not connected. Now those turn out to be important for this next theorem. If we have a set that is both open and connected, then we can make some nice conclusions if we have the right sorts of functions to start with. So here's the theorem. Let F be a continuous vector field on the open connected set D. And I'm going to put that in R2 for now. If path integral over C of f dot dr is independent of path, so knowing the endpoints of C, I can go between them however I want, and I'll get the same result. So that's what it means to be independent of path in D. Then F is in fact conservative on D. So this tells us, so it may be tricky, if I just hand you a vector field, it may be tricky to decide whether or not that vector field is conservative. Here's a theorem that can help us figure that out though. If this path integral is independent of path, and D is both open and connected, and the vector field is continuous, then yeah, it is conservative. It is the gradient of something. So the proof is a little tedious, so I'm going to refer you to the book for that. But I do want to give you a brief indication of how to prove it. To show that a vector field is conservative, you need to come up with, or show that you can come up with, a potential function for it. So I'm just going to define this function, f of xy, to be the path integral from ab to xy of f dot dr. AB will be some specific point in D. XY is whatever point you want to know the value of little f at. This is independent of path, so I can use this funny looking notation, right? I'm not doing it over some specific curve C, because the curve C doesn't matter. It's independent of path. And the rest of the proof, once you've defined this f, the rest of the proof is showing that, in fact, the gradient of f, of little f, is big F. And that's what you can read the book for. I'm not going to go through it, but that's the idea. All right, here is now an easier, at least partial test to decide whether you have a conservative vector field. This one is useful theoretically, but not so useful practically, because you can't parameterize every possible curve between 2 points, between 2 arbitrary points in D. So we need something a little easier to apply. Let's let capital F of xy equal p of xy, comma, q of xy. If f is conservative and p and q have continuous partials on D, an open connected region, same kind of D we had in the previous theorem, then p sub y equals q sub x on D. Now, this gives us a partial test for conservatism. If we have a conservative vector field, these things must be equal. The contrapositive of that, that's a logical a statement that's connected in a way to this one through logic. If these things are not equal, then f cannot be conservative. If these are equal, then there's a chance that f is conservative, and it might be worth looking for a potential function. Now, this one we can prove, actually. So, since f is conservative in our assumptions here, f looks like the gradient of some function little f. But that's also equal to pq, by the way we set this up. And therefore, p sub y, that's fxy, which is equal to fyx, because remember we assumed that p and q have continuous partials, which means that the second partial, these mixed partials of f, are continuous. And if they're continuous, they're equal by Clairaut's theorem. Well, fyx, that's q sub x. So there's not much to that proof. It would be really nice if we could reverse this, if we could say when these guys are equal, f is conservative, instead of just, well, if f's conservative, then they're equal. It would be nice if we could make it an if and only if. So that's our next task. And to do that, we're going to have to introduce a couple more topological notions. First, curve is called simple if it does not, if it does not intersect itself except possibly at the endpoints. So this curve is not simple. This curve, however, whoops, not that curve. This curve, however, I like drawing these. This curve, careful, is simple. These don't actually meet here. That curve is simple. So simple is a technical property, right? It says that the curve can't intersect itself, except it could meet up at the endpoints, that's okay. But it can't cross over itself in the middle. Okay? So it doesn't mean it's not complicated if it's simple. This is a complicated curve. What it means is that it doesn't intersect itself except possibly at the endpoints. The next topological idea is that of a region being simply connected. So definition. A connected region, D, say, is called simply connected if every simple closed curve, SCC, simple closed curve, okay, so we just defined simple, we already know what closed is. Every simple closed curve in D encloses only points of D. So here it is a simply connected region. Because no matter what simple closed curve I draw in here, inside that curve are only points of D. But if I take a region like this, with a hole in the middle, so the points in the middle here are not part of the region, that's not simply connected because this simple closed curve encloses points that are not part of the region. So you can kind of get an intuitive idea about what simply connected means by just thinking about a region that doesn't have any holes. If there's a hole in the region, you draw a curve around it, and then you've enclosed something that's not part of the region. If there are no holes, then you can't do that. Here is our next theorem now. This is going to be a useful one for us. This is a test for conservatism. for, not far, test for conservatism. Let f of xy equal this vector field, p of xy, comma, q of xy, on an open, simply connected region D. If P and Q have continuous first partials, on D, and P sub y equals Q sub x on D, then F is in fact conservative on the region D. So this gives us a converse to our original, our earlier partial test for conservatism. It says, if P sub y equals Q sub x, then F's going to be conservative as long as you're doing this on an open, simply connected region and partials of P and Q are continuous. So things have to be kind of nice. You can't have holes in the region has to be open, and the P and Q have to have continuous partials. The proof of this is postponed. We will prove it later, after we develop some more tools to work with. So we're going to come back to it. But let's try an example. Let's just see if we can determine whether a given vector field is conservative. So let's say that capital F is x squared, comma y to the fourth. Is that conservative, is the question. You should pause here, think through the theorem, and see whether you can apply it. All right, well, the domain of this is R2. That is both open and simply connected. So check, check. So we have those. The components of F, P, the P and the Q, are polynomials, so they have continuous partials. P, Q have continuous partials. So check, I guess. And so the theorem applies. Right, we're on an open, simply connected region. We have continuous first partials. The last thing we have to check is, does P sub y equal Q sub x? Right, P sub y is 0, and so is Q sub x. So check. And therefore, F is conservative, according to our test for conservatism. Now that's a pretty easy test to apply. What's nice about it here is that it tells us, because we have passed that test, it tells us that F does in fact have a potential function, so it's worthwhile trying to find it. If I didn't know that F was conservative, I could spend a lot of time trying to find a potential function when there wasn't one. I would just waste my time. Now I know that it won't be a waste of time. There is in fact a potential function out there somewhere for this capital F. Let's find it. Let's find little f such that the gradient of little f is big F. This is a kind of a puzzle. You should pause here and try it and see if you can do it without any hints from me. Now I'm going to give some hints. All right. Capital F looks like PQ. In this case, that is x squared comma y to the fourth. But remember, P is the partial of f with respect to x, right, because capital F is the gradient of little f, and Q is the partial of f with respect to y. So we get this system of differential equations. Fx equals x squared, and Fy equals y to the fourth. And so I can recover f by integrating this with respect to x. So f of xy equals integral x squared dx. I'm integrating with respect to x because to get this, I had differentiated with respect to x. And so I get a 1/3 x cubed Remember your plus c? The plus c really matters here. It makes a huge difference as to whether or not this is even going to be possible. The thing is, this was a partial derivative. This fx was a partial derivative. So plus c is a little bit more, is a little bit broader than it was in Calc 2. It's really plus some function of y, possibly. Because if I differentiate this, I'm holding y constant. So this, a function of y alone, acts like a constant. So I have to remember that there's possibly something there that looks like that. My second differential equation here says f of xy is equal to integral of y squared, y to the fourth, dy. It's dy because this came from differentiating with respect to y. So this is a 1/5 y to the fifth plus a constant. But that constant could be a function of x, actually. Not strictly constant, but constant with respect to y. Okay, so both of these are supposed to be the same f. They don't look the same at all, though, right? But they have to look like this, and they have to exist because I know that my vector field is conservative. It passed the test. It passed the test for conservatism. So somehow these have to be the same function. Well, here's how. This function of x alone, that's 1/3 x cubed. This function of y alone, g of y, that's 1/5 x to the fifth. So I will let f of xy equal 1/3 x cubed plus 1/5 y to the fifth. Now there could be an actual plus c, plus a constant, because this g of y could be 1/5 y to the fifth plus a constant. But I just need any old function whose gradient is my given vector field. So the plus c won't change that. So I'm just going to go with this simplest possible thing here, where my constant c is 0. You should check this. You should pause here. Confirm for yourself that the gradient of this function of two variables is in fact my vector field capital F. And now say I wanted to do a path integral from, I don't know, let's go -1, -1, down here, up to 3, 4, say. And my path is this terrible thing. I have no hope of parameterizing that path because I just made it up. It could be anything at all. But I can do a path integral along it anyway, at least of this vector field. Path integral over c of f dot dr. And this should be a hint to you, by the way. If you run across a path like this that there's no hope of parameterizing, you better hope your vector field's conservative and that you can find a potential function for it, as we did, so that you can apply the fundamental theorem for line integrals. This is, I'm not even going to try to do the parameterization intermediate step. I'm just going to cut right to the chase. This is going to be 1/3 x cubed plus 1/5 y to the fifth, evaluated from -1, -1, up to 3, 4, the top point. And then I just plug in and subtract. It's great. Great, great, great. This is 1/3 times x cubed, it's 27, plus 1/5 times y to the fifth, minus 1/3 times -1 cubed, plus 1/5 times -1 to the fifth. And that comes out to be some number. It's not going to be a terribly pleasant number. I'm just going to leave it at that. But you can see what an advantage it is to have a vector field that you already know is conservative, because you can find a potential function for it and then apply the fundamental theorem for line integrals, regardless of whether you're able to parameterize the path. Now, if I'm given a path that I can parameterize, then I have a choice, right? I can go ahead and parameterize the path and compute the path integral the way we used to, Or, if I have a conservative vector field, I can find this potential function, hopefully, and just apply the fundamental theorem for line integrals. But when you have a choice, go with the easier way. Now, we'll do some more examples of this in class, and I'll let you go to the board and try your skill at it. But I want to wrap up this lecture with a discussion of why we use the terminology we use. Why are these kinds of vector fields called conservative? Now, here's why. Let's think about our vector field f of r of t. So I'm looking at the vector field over some curve parameterized by r of t. And let's just say that this is m r double prime of t. So this is F equals ma. So we're talking about a force, and r double prime is acceleration, m is mass. So this is Newton's second law. Then the work done in moving in moving some particle along this path c, along a path c like this, by this force F, is going to be the path integral over c of f dot dr. Like so. And since I know what f looks like, I can go ahead and make this substitution here. That's m r double prime of t dot r prime of t dt. And if you squint your eyes up just right, you can recognize this as being pretty much the derivative of r prime of t squared. So I'm going to write it in here, and then we'll investigate it and see why that's correct. I shouldn't say squared, I mean dot with itself. Okay. If I take the derivative of this, I can apply the product rule for dot products, the dot product rule, and I'll get the derivative of the first, r double prime, dot the second, r prime, plus the derivative of the second, r double prime, dot the first, r prime. But the dot product's commutative, so really both of those terms are r double prime dot r prime. So when I take the derivative of this, I get 2 r double prime dot r prime, which is why I put that 2 in the denominator out there. That cancels, and I just get this back. And I know how to compute this integral here. Oh, and I should, sorry, I forgot, I had gone to the dt, so these should no longer be c's, these should be from a to b. Where the bottom point here is r of a, and the top point is r of b. Once I'm integrating with respect to t, I need to have my t limits. Okay, well I'm integrating the derivative of something with respect to t with respect to t. So this is going to be m over 2 times r prime of t dot r prime of t, or put another way, from a to b. Put another way, you remember what happens when you take the dot product of a vector with itself? You get the square of the magnitude. So this is m over 2 times the magnitude of r prime of b squared minus the magnitude of the r prime of a squared. But the magnitude of r prime is the velocity. The magnitude of the velocity is the speed. So this is 1/2 m v of b squared minus 1/2 m v of a squared. You remember from physics 1/2 mv squared as the kinetic energy of a particle? So what this tells me is the work done by F in moving my particle from the beginning point to the ending point is equal to the change in kinetic energy. Right? Here's my kinetic energy at the end, here's my kinetic energy at the beginning, and I have subtracted them. So let me call this, I'm going to write this just slightly differently. I'm going to make this k of v minus k of a. So the k is for kinetic energy, the b is this point, and the a is the initial point. B is the final point, a is the initial point. So when I look at that, I can see my change in kinetic energy just sitting there. Now that's what I get if I compute this path integral by parameterizing the curve. What if f happens to be a conservative vector field? If f is conservative, then it looks like the gradient of some function little f. And I can compute the same path integral by applying the fundamental theorem for line integrals. So my path integral over C of f dot dr is going to equal path integral over C of the gradient of little f dot dr. And I'm going to introduce a new notation here. This is going to be the path integral over C of negative gradient of P dot dr. So P is equal to negative f. I just changed the sign on this. And P is called the potential energy of the object. So this tells us why we're using the term potential function for f. It's because it's related to this idea of potential energy for whatever it is we're moving, this particle we're moving. Now, at this point, this is where I want to apply my fundamental theorem for line integrals. This is going to be negative p at the end, which is b, minus p at a, which is negative p of b plus p of a. And because these both represent the same integral, I got these two different results here. Oh, and by the way, this negative p of a plus p of b, this also represents the change in potential energy. It's the negative of the change in potential energy. But because these two things both represent the same integral, they have to be equal to each other. So therefore, k of b minus k of a is equal to negative p of b plus p of a. And here's where the magic happens. I'm going to put the b's on one side and the a's on the other side. So I get k of b plus p of b is equal to k of a plus p of a. And I see that energy is conserved. It's awesome. Right? This is the total energy at the end. Energy. This is the total energy at the end. My kinetic energy plus my potential energy. That's all I've got. It's the same at the end as it was at the beginning. Energy was conserved. So that's why we call these conservative vector fields. If f is a conservative vector field, if my force is given by a conservative vector field, then when I look at the work done by that force, I have the same total energy at the beginning as I have at the end. Whatever I gain in kinetic energy, I lose in potential energy, and vice versa. So the total energy in the system remains the same. And that's why we use this terminology. Here's a summary of what we have. First of all, we can talk about f being conservative. And that means one specific thing, that it is the gradient of some function. We can also talk about the path integral over C of f dot dr being independent of path. And for this, we need to be in an open, connected region. Okay. If we happen to have this independent of path in an open and connected region, then we will see that f is conservative. And independent of path means pick any 2 points in the region and connect them with any path in the region. And you have to get the same, well, once you've picked your 2 points, pick any path. Every path you choose has to give you the same answer. Now if you pick different points, you can get a different answer, of course. But for the same endpoints, the path can't matter. Path integral over C of f dot dr is 0 for any closed path, again, this is for an open connected region. If that happens, then in fact f is conservative. And for, we have p sub y equals q sub x, where p sub y and q sub x are both continuous. And in this case, we need an open and simply connected region. If any one of these, 2, 3, or 4 happens, then the first one happens also, and vice versa. So these are all different ways of talking about functions being conservative. Now vector fields being conservative. Conservative vector fields are one of the really important things that we study in this class. So we're going to spend a lot of time thinking about what conservative vector fields look like and how they behave. And we'll do more examples of this in class and spend some more time on it. And in the meantime, work hard. I'll see you in class.